In the last video, we saw polynomials of degree 2. Now we have polynomials of any degree. So it could be degree 1, or degree 2, or degree 3. And we're going to see it from a little different perspective. We're going to focus on the zeros and behavior, multiplicity of zeros, which has to do with zeros, and y-intercept. Y-intercept. Zeros are the same thing, well, as the x-intercepts, or they're closely related to x-intercepts, so that already is covered in zeros. Zeros are the same thing as roots, or related to x-intercepts. They're almost synonymous. X-intercepts are usually points. So let me write that down. So x-intercepts, intercept points, are sort of zeros, which is the same thing as roots of a polynomial. Okay, so in my experience, the best way to show all of this is with examples. Oh, before we continue, there's a new notation we're going to use for the end behavior. I have not explained what end behavior is yet, but I will. Actually, let's start with that. End behavior. And behavior. And we're going to have, in addition to the new idea of end behavior, we want to have a new notation. New notation. Okay, so there's the new notation. And we're going to explain two end behaviors on the right and two end behaviors on the left. Yeah, so pretend you have a function, and we don't know what's going on with that function. Let's do an example. We don't know what's going on with that function. You know, I'm going to put a cloud, so we don't know what's going on here in the function. But eventually, the function does this. And let's say on the left, it does that also the other way. Okay. So what happens in between? We don't know if there's vertical asymptotes. We don't know if it goes up and down. We don't know what happens in between. And by in between, we mean this range, which we cannot see, could be as short as 1 unit, or even shorter than 1 unit, or it can be 1,000,000 units. It doesn't matter. What matters is that eventually this behavior starts occurring and it does not change. It has the same pattern. In other words, it curves up and it goes to the right and up. The way we describe this behavior, and this is a new notation, it looks kind of weird, but this is the way it is. By the way, we're going to label this as a function f of x. So this is f of x. And the way we describe this behavior is by writing down LIM f of x, as x goes to infinity equals infinity. I know this is a little confusing because it is completely new. So this means to the right, the function goes up, 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 up without bound, without stopping, and to the right without stopping whatsoever, and without bound. Without bound is a better description than without stopping. Going up with, so yeah, let me introduce the idea of bounded versus up without interruption, or going up forever. That's what I mean by without interruption. Bounded versus up without interruption. So pretend you have an asymptote and pretend a function does this. And it gets closer and closer to the asymptote, to the horizontal asymptote. This is going up without interruption. That's what we mean by this. So this is up, and up and up. It keeps going up and up, but every time it goes up, every time it increases by less and less and less. Okay. Versus, now, while this is going up, it is bounded. You see, even though this is going up and up and up forever, it does not break the ceiling. So I didn't mean to put down versus. What I meant to say is, yeah, even though graph goes up forever, the graph does have a ceiling. That's very, very important. So it never breaks the ceiling. It goes up, it gets closer and closer and closer, and yet it never breaks the ceiling. Okay, that's not what we mean with this notation. That notation does not include this. So that's the one thing I want to emphasize. No. When we put infinity here, that means that there is no ceiling. So the notation, oops, I meant to put the notation. Okay, limit. So this means LIM means limit of f of x as x goes to infinity equals infinity, means there is no ceiling as we go to the far right. So as you go farther and farther away to the right, there is no ceiling. Okay, and before we get all panicking about this end behavior and this limit, let me assure you there's only going to be 4 things we're going to look at. So this is one of the 4. This one is one of the 4. The other 2 are going to be variations of this one. So once you know this one and the variations, you are set. Don't panic too much because yes, this is new, but it's not overly difficult right now, not yet. It won't be, and even in calculus, we just got to make sure we study this carefully. It is a little bit difficult, but not too much really. Anyway, so this end behavior means right up. This behavior that it's shown in here is left up. So I'm going to write it here in the example. So the way we describe this end behavior on the left is by writing the limit of the function as x approaches negative infinity. So that means on the far left is infinity, up. So far left versus far right, up and up. And then we have variations. We have all 4 variations. See, I'm beginning to get ink on my hand. Anyway, 4 variations. We got left, right, that's 2, and then up or down. We haven't shown you an example where things go down. So let's look at an example. Example 2, you got a function f of x. What happens in between? And in between, again, is relative. In between the 2 extremes. We don't know. This could be 1 inch, or it could be a million miles. We don't know. If the function eventually does this, for instance, those are what we call the end behaviors. Boy, they look like arms. I almost want to draw legs. But no. These are the end behaviors of the function. Who knows what happens in here? You could go have vertical asymptotes, or you could, the function could be waving up and down. It doesn't matter. But eventually, if the behavior stabilizes and becomes this kind of behavior, the way we describe this is the limit of the function. So we have to have all of those parts in it as x goes to the far left is down. So left down, the limit of the function as x goes to the far right is also down. Yep. Now, the way the graph curves doesn't have to be this way. So same as, I'm going to give you a new picture. It could be that the graph goes this way and this way. As long as it is clear, this kind of looks like it's curving up a little bit, or maybe stabilizing a little bit. So I want to kind of draw it a little lower. This one does look like it's going lower. So maybe something like this is a little better. Yeah. So the same thing applies here and here. To the left we go down, to the right we go down. So the way things curve doesn't matter. It can curve down this way or curve up. This is called curving up. Even though the graph is going down, it's technically it is concave up, while this is concave down. So this is concave up. You can have a concave up graph that is going down. Yeah. In more elementary courses, not necessarily more elementary, but in other courses, instead of writing all of this fancy notation, I just call this right up in behavior, and this is left up in behavior. This is the same thing. It's just much more fancy. Same thing with this. This would be right down in behavior, left down in behavior. So if you want to start using this initially, that's fine, as long as we can translate into this. This is a fancy way of doing it. It is not so fancy in the sense that it is more precise, because with this notation, then we can also indicate other kinds of behavior that are happening that could happen. But those are the two. And then you can have combinations. So example 3, I'm going to try to squeeze it here. You got a function, and maybe and the function f of x goes this way and this way, going up, and left. So we'll just have a combination of the two. So in this case, the limit of the function, I know this is kind of long, as x goes to the right is up. So remember, this symbol means up when it is the output of a function. This symbol means right. So it is the same symbol, infinity. Those two are the same, but they have different meanings depending on where they are placed. If this is the output of the function under the limit, then that means up. If it is by the x, that means to the far, far right. Here we have the limit of the function as x goes to the far left, and it is down. And then you have, might just as well put a fourth example, which could have, okay, up on the left and down on the right. So as I'm doing this, you can probably start thinking, when I'm doing examples like this, it is not a bad idea to pause the video for a moment and say, hey, let me see if I can do this. Sometimes I feel like pausing myself the video and then asking you and then giving you some time, but I don't want to do that, because then the video will look too much like those videos where, there's that video or that show where there is a girl and she pauses for, it's a children's show, and she pauses for other people to say what's going on. Anyway, so this is going down. Oops, there's no much room here to write this, but it's negative infinity. There we go. As x goes to the far right. And so this is the way we describe this behavior. this should go a little farther to the right. Um, in some parts of this, we have to be particularly precise. I'm going to change this a little bit because this arrow should point a little bit that way, a little more, indicating that we're going, even though it's curving this way down, we're still going to the right without any um, limit, without any boundary. And this is a limit of the function. I didn't give myself enough room to put the answer here. So I'm going to put to infinity as x goes to negative infinity. Okay. So again, far left, up, far right, down. Remember those, please. That they are very important. Um, yeah, yeah. Oh, if we have a vertical asymptote, then that doesn't count. So vertical asymptotes do not count as end behaviors. In this video, we're not going to see vertical asymptotes, but if we were to have a vertical asymptote in a function like this, you know, who knows what happens here? We don't know, and we don't care for purposes of this portion. This is not, so if we put down the limit f of x as x goes to the far right equals up, that's wrong. That would be wrong. Because this is not the far right. We have a wall. If we have a wall, that's not the far right. Far right means no wall. We can just keep going to the right, on and on and on. That's why here I wanted to emphasize that that the arrow, you know, has to point a little bit to the right, because that means that the graph keeps going right and down without any wall that will stop it. Here, this wall stops it. And well, stopping is misleading, because this graph keeps going to the right, closer and closer and closer. It keeps moving ever so little, but still to the right. So technically, it doesn't stop, but it has a bound. See, that's what I want. You can get closer and closer to the bound, but if there's a bound, this does not apply anymore, because what fails in this case is not this guy. What fails is that this doesn't go to infinity. Infinity means no bound. As the name says, infinity. So that, you know, finite, finished, end. So this means end. And in this case means without. So without end. And this would be an end to the motion going forward. And this is what we mean. Move forward. Forward is that way, without ending. Yeah, but then you could say, well, this is not ending, moving forward. What we mean in this case, without bound. Yeah, that's probably more, even though, yeah, that's what we mean, without bound. Anyway, so be aware of that. Now let's move on to the actual polynomials. So that was the idea of end behavior. Let's do a whole bunch of examples about polynomials. So the easiest polynomials are going to be things like x minus 5. Okay, so that is a polynomial of degree 1. So the way we graph this polynomial is very straightforward. It goes like this. End behavior on the right is up. Left behavior on the left is down. I don't want to dwell too much on the end behavior, because then we lose track of the new idea I'm trying to explain. So I'm going to put the end behavior to the side for the moment, but there is an end behavior going on. This means up, right. You know, I'm going to, I have mixed feelings, because on one hand, it is important to emphasize the end behavior. On the other hand, I don't want to distract ourselves from the new idea I'm trying to introduce. So again, let's put the end behavior to the side for now. I'm just going to mention it on the examples, but I'm not going to write them down. So this would mean that the limit of the function of this function as x goes to infinity is infinity. And the way we write this end behavior is that the limit of the function as x goes to negative infinity is negative infinity. Okay. Now, the 0 is 5. That's what the line goes through. And the y-intercept is another thing that I don't want to dwell too much on this, because I want to introduce the idea of zeros and how these zeros affect the graph. So there it is. Okay. So that was example 5. Example 6. If you have 3 zeros that are the same, so x minus 5 times x minus 5 times x minus 5. So I'm going to write it as x minus 5 times x minus 5, which mostly, or most of the time, we write as x minus 5 with the exponent of 3. We still have the same picture, except that it is twisted. We still have the same end behavior, right up, left down, through the number 5, through the 0, 5. What is different is the multiplicity. See, the 5 is a 0 once. Here, we say that the 5 is a 0 3 times. Three times. Yeah. So the multiplicity of this 0 is 3. Multiplicity of 5 is 3, because it shows up. And the difference that it makes is that the graph is twisted there at 5. It has a twist to it. It still has the same kind of behavior. Well, once it's twisted, it becomes curved, and it stays curved on and forever and ever. Yeah. Okay. So if we have x to the 5, x minus 5 to the 5, so f of x equals x minus 5 to the 5, we still have the same graph, except that the twisting is a little more pronounced. So it is a little flatter. Yep. And this is still 5, but the multiplicity is 5. So multiplicity of this 0 is 5. Now this 0 is 5. That's a little confusing. And its multiplicity is 5 as well. Yeah, that's kind of confusing that we're using the same number. The exponent gives us the multiplicity, and 5, what causes this to be 0 is the 0 itself. Okay. And then if we have 7, we will have the same, even a little flatter towards the 5. And then 9, same thing, even more flat, and so forth. Okay, 7. Okay, so we have 1 0 with a large multiplicity. Now, what if we have 2 zeros? Example 8. If we have 2 zeros that are different, say f of x equals x minus 5, x minus 10, then we're going to cross the x-axis twice. Once at 5 and another time at 10. Okay, and there's the graph. It's a parabola, as you probably know. When you multiply the two x's, we're going to end up with x squared, which causes us to have a polynomial of degree 2, which is a parabola. So we're going to have a vertex, there is symmetry, and other things going on. And there we have it. Again, the end behavior on the right is going to be up. The left behavior is going to be up as well, as opposed to this case where we have right up left down, right up, left up. There's only 4 possibilities: right up, right down, left down, and then the combinations of right and left, up or down. Anyway, so there we go. 9. What if we have 3? F of x equals, say, x minus 5, x minus 10, x minus 15. Okay, we got 3 zeros. Here we have 2 zeros, each one of them single multiplicity. Multiplicity is 1 for each one of the zeros. Now we got 3 zeros, still with single multiplicity. Okay, so the graph will be through the 5, through the 10, through the 15. So this will be 10, 5, 15. Okay, we got 3 zeros, each one of multiplicity 1. And the end behavior on the right is up. The end behavior on the left is down. Okay. Before I move on, well, I'm going to move on, but I want to show you. Well, no, let's move on. 10. Okay. What if we have 4? X minus 5, x minus 10, x minus 15. You can probably guess the next one, x minus 20. All right. The graph is going to go through 5, 10, 15, 20. So 5, 10, 15, 20. Okay, so we have 4 zeros. We go through the x-axis. The end behavior on the right is up. The left behavior on the left is up as well. 11. F of x equals x minus 5, x minus 10, x minus 15, x minus 20, x minus, if you had to guess, 25. Now we got 1, 2, 3, 4, 5 zeros, each one of them with multiplicity 1. Can you tell what the graph is going to look like? 5, 10, 15, 20, 25. There we go. So it is the same pattern. If you look at 5, 10, 5, 10, 15, 5, 10, 15, 20, 5, 10, 15, 20, 25. Well, let's do one more. 12. X minus 5, x minus 10, x minus 15, x minus 20, x minus 25. And I have to squeeze in here x minus 30. Well, you can probably guess what this is going to look like. 5, 10, 15. I lost track. 5, 10, 15, 20, 25, 30. There we go. This should be a little farther to the right. There you go. And there. So we got 5, 10, 15, 20, 25, 30. There we go. Well, I hope we have a pattern going on. Notice that on all of them, the end behavior on the right is up, 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 up. And what changes is the tail. You know, pretend that is the head of a whatever, a snake or whatever. So the tail is up when we have 2. The tail is down when we got 3. The tail is up when we got 4. Down 5, up 6. So every even number of factors, the tail is up. And every odd number of factors, the tail is down. Okay. Is that always going to be the case? Well, sort of. If we don't have an extra negative outside, and if all the x's have positive coefficients, yes. This can easily change. Let's look at problem 9 or example 9. I'm going to make a new example, example 13, using example 9. So I'm not going to copy, well, I'm going to copy this, but I'm going to change it. We're going to put a negative on it. X minus 5. So the same function, except that we're going to add an extra negative in front of the whole thing. X minus 10, X minus 15. So remember what the negative does? We had a video on the transformations of functions. If you put a negative in front of a already existing function, what it does is that it reflects the function over the x-axis. So we have the same exact picture, but we have to flip it the other way. Well, we don't see through the paper, but it's going to flip. So the picture is going to do this instead. So we're going to still go through 5, 10, and 15, 5, 10, and 15, but the graph is going to have a right-end behavior going down and a left-end behavior going up. So that's how we alter this situation of going up on the right all the time. So now the head is going down and the tail is going up, even though we have 3 zeros. Okay. Now, let me emphasize that we are drawing sketches. I spoke about sketches in, I think, the last video, but I want to say more about sketches. Remember, I'm going to compare what I'm going to do next with, with this example 9. So I'm just going to copy example 9 again. 9, so recall, 9 was f of x equals x minus 5, x minus 10, x minus 15. And let's just recall the graph. Oops, I didn't mean to put a vertical line. There. So we go through 5, 10, 15, 5, 10, 15. Those are the zeros. That's a sketch, a good sketch. Although we should probably add the y-intercept to the sketch. And that's about it. And then we have to establish the end behaviors. But I don't want to make a big deal about those because I want to look at the zeros. The one thing I want to point out to you now is this example. So this is 9, which I want to compare to 14. Say you have x minus 5, x minus 10, and to exaggerate, x minus 15,000. How many zeros did I put? One, yep, 15,000. So same kind of zeros, 5, 10, but instead of 15, I'm putting down 15,000. Okay. The sketch we're going to draw for that is going to be the same sketch. 5, 10, 15,000. Now, you're going to say, wait a minute, that doesn't make sense. How come this distance is 5? You know, from 5 to 10, there's 5 in between. From 10 to this is going to be 14,990. It doesn't make sense that this is 5 and this is 14,990. Well, no, it doesn't make sense. You are right. However, we are drawing a sketch. A good sketch shows the important parts of a graph, even though we have to break up the scaling of the graph. That's what a good sketch does. I mentioned in the last video the planetary system that we see in books, science books. You know, they got the planets, and the planets are like this far apart from one another in the picture, which doesn't make any sense at all, because if they were that close, I mean, they'll just gravitate towards each other, and that will cause a huge collision, and you know, that doesn't make sense. The distances between the planets is gigantic. If you actually draw an accurate picture to scale of the planets, it would be, you wouldn't be able to see the planets. So the scale of the picture is off. That doesn't mean it is a bad picture. We just have to be aware of the scale. The picture is good because it tells us what's going on. It shows the 9 planets or whichever, the 8 planets, um, and the orbits and all that. It does a good job showing the planets, but we have to be aware that the scale is off. Same thing happens here. This shows us that there is a bump, there is a gap here between 5 and 10. And then there's a gigantic big gap, even though it doesn't show the proportion of the difference of the gaps, between 10 and 15,000. See, if we were to graph this function on a graphing calculator like this one, there's 2 things that could happen. I'm not going to show you, but because I don't want to spend that much time on it. But there are 2 things that could happen. If you zoom out so you can see this gap, the graph is probably going to look like this. You're going to be able to see this gap, but you won't be able to see this one because this is so small in comparing to that, in the real picture. It would look like we're just touching the x-axis. We're not actually going through the x-axis. So zooming out will show this beautifully, but it won't show this at all. Do the experiment. If you have a graphing calculator, put this function and zoom out so you can see this, and that will look good, except that we won't see this part anymore. So zooming out messes up this part. If we zoom in so that we can see this bump, that's cool. But then we won't be able to see the other bump because the other one is going to be so far away, it's not going to fit into the picture. And if you make it fit into the picture, then you're going to end up with this picture. So zooming in is going to give you this picture, and you won't see the other bump. That's why we want a good sketch. The good sketch will show us everything that is going on, all the crossing through the x-axis. Okay? So for purposes of drawing sketches of polynomials, if the distances are short or long, just kind of use your best judgment, but don't necessarily do things to scale. The whole point of this sketching is precisely not to draw to scale, because we have technology that can do that quickly and easily, but then we may be missing what's going on with a polynomial. A precise picture is not necessarily a best picture. 15. Having said that, okay, let's show what happens when we have, say, x minus 5, so a function equaling x minus 5 squared. But let me do this as a progression. So I'm not going to show you how to do this right away. I'm going to do a progression of things that are going to approach this function. So let's say, so right now I'm going to give you different examples. Let's say you have x minus 5 times x minus 6. Okay, so that's a parabola. And I'm not giving a name to this function because what is important of this progression is the actual factors, not the names. Anyway, so you got 5 and 6. Now, if we have x minus 5 times x minus 5.1, now this is what I'm going to do is going to contradict what I just said earlier, then that the picture should be the same. But the reason why I'm contradicting myself for a moment is so that we can see what's going on with x minus 5 quantity squared. So I'm aware there is a little contradiction. Okay, so if I was going to do this, keeping the scale correct, okay, so that is, or attempting to keep scale, keeping scale correct, then we would go through the 5, and then right away we have to turn. So 5, 5.1. Now, if we did x minus 5 and x minus 5.01. Okay, so now I almost wouldn't be able to see because as soon as I cross through the 5, I have to turn around and come back. So one x-intercept would be 5, or 1, 0 is 5. The other one is almost next to it, 5.01. And if we have x minus 5, x minus 5.001, well, the pixels, the ink is not fine enough to actually show the gap. And again, I'm breaking my rule. This is not a sketch. This would be more correct to scale, even though I'm already seeing that it's probably not, but assuming it was, this is what would be happening. So now let's think about it. When we have x minus 5, finally, times x minus 5, the gap closes up. So here we have a gap. The gap is smaller, even smaller, very tiny. And when we get to this point, it closes. So the graph bounces off the x-axis, touching the x-axis at 5, and that's it. There's no gap. There's no dip under the x-axis. It just stays on the x-axis. It's just like a ball. You throw a ball on the floor. The ball doesn't go through the floor, usually. And so it just bounces off. That's exactly what it is. It just bounces off the x-axis. It does touch the x-axis. It does have a point in common, which would be 5, 0 in this case. But it bounces off. So if we have x minus, so let's draw the picture. You already knew that because it was a parabola shifted to the right if we have x minus 5 squared. But this shows it in a different view, in a different perspective. Okay, so example 16. So, well, actually, it is the same example. I was leading to it, 15. Yep. Yeah, I want to stay with example 15 and just provide a more proper, even though we already did. So this is 15. Okay. X minus 5 quantity squared. It is just a graph that bounces off the 5. The end behavior is the same. Up to the right up, left up. Okay. What if we have, this is 15, 16 alpha of x equals x minus 5 to the 4. We already saw what happens with x minus 5 cubed. By the way, this is 0 of multiplicity 2. So the 0 has multiplicity 2. Now the 5 is going to have multiplicity 4, sorry. And it is very much the same, except that it's a little flatter. It's a little more flat on the 5. So it's a little more, I don't want to say wider, I want to say flat around the 5. So again, the 5, there's only one root, 1, 0, but this time the multiplicity is 4. Multiplicity 4. And if you put a 6, then it's flatter and flatter. One thing I recommend, if you have a graphing calculator like this one or something similar to that, is to actually graph those functions. Play with it. Be curious about it. Challenge me. Say, hey, he said it's a little flatter. I believe him, but I want to double check. And so draw the picture with a graphing calculator and see, oh yeah, he was right. Yeah. And it's not necessarily that I want to mislead you, but me and anybody else can make mistakes anytime. And so it is a good idea for students. We encourage students to, in a good way, to challenge what we do, to challenge what we tell you. Hey, is he right? That doesn't seem right. Let me check. Oh yeah, he's right. Oh no, he made a mistake here or a mistake there. That's a healthy thing to do, to intellectually, as long as we are, in respectful, to say, hey, Mr. Saldivar, I didn't get this answer, I didn't get this or that, or I got this other answer, and then I can check, and oh, sure enough, I made a mistake somewhere. So that is a good thing to check what people do. Okay, let's get into combinations now. So let's say you have x minus 5 squared, x minus 10. Now we're going to combine different zeros, some of them with multiplicity, others with no multiplicity. Well, actually, this is multiplicity 1. So all of them have multiplicity. When they have multiplicity 1, we many times say that they don't have multiplicity, but that is actually wrong because there's multiplicity 1. So, okay. So that means that we bounce off. See, I know that this polynomial is of degree 3. So a degree 3 polynomial kind of goes like this. It's sort of a snake with a head up and the tail down. Except that, and how do I know that? Because that's the way they sort of behave. Boy, there's a lot of sheets. So there's 1, and then we got 2, and then we got, see, 3, and then we got 4, and then 5. So that's the most that we could have. I mean, the most turns that we could have with 5 factors or 6 factors, 1, So I know this is going to behave this way, and we're going to go through 5, but not through the x-axis. We're going to bounce off the x-axis, and then we're going to go through the 10. So this is going to be 5, while this is going to be 10. And we're not going to go through the x-axis. See, that's why it is important to have a good sketch and to be aware that we have a good sketch. Let's say this was 1,000, just for sake of argument. We still will end up with the same sketch because I want to show that nothing is happening here. See, if we do things properly to scale, and we have a little itty bitty gap here, a little bitty crossing of the x-axis up and then down, in the big picture, we would lose that piece of information if we had a big number here. So that's why we want to focus on the sketch. The sketch is going to give us all and every one of the parts that are important about the picture. And that way we don't have to worry about the scaling. Yeah. So sometimes, many times in fact, not being precise, it can be a good thing. Precise as far as the scaling. The sketch can give us more information. It's just like in accounting. In accounting, you can provide every single piece of information. Let's say you have a big store, a grocery store, and and somebody comes and wants to check the balance sheet of a grocery store. They don't want to know whether they sold a candy bar or 2 candy bars. They don't want to know that. They just want to know, okay, what is the revenue? What are my costs? What is my profit, and so forth? How did the profit change from one month to another? In the big picture, I don't want to know whether a candy bar was sold, at 3 in the morning or 5 in the morning. I don't want to necessarily know that. Same thing here. We want to know what is going on in general. Are we going to cross the x-axis and have a little bit of a gap or not? Kind of like this, but on the other side. Here, we're establishing, no, there isn't. We just go, the graph bounces off the 5, and then we do have a gap. That's what I call the big picture. That's what I mean by a sketch. So many, many times we don't want to be totally and completely precise. 17. 18. So what if we have x minus 5 single, x minus 10 double, say x minus 15 triple. So we got 6 roots. Well, technically, no. There's 3 roots, 5, 10, or 3 zeros. 5, 10, and 15, those are 3 zeros. However, this is single, double, multiplicity 2, triple, multiplicity 3. Every time we have an odd multiplicity, the line or the graph goes through, and every time we have an even, we bounce off. This is multiplicity 6, so then I'm expecting something that comes down, and it bounces, and then it goes up eventually. So through the 5, bounces off the 10, through the 15. Now, this cube means that when we go through the 15, we're going to kind of twist it a little bit. That's the only thing that is different. Yeah. And usually when I'm grading things like this, I don't pay too much of a close attention to the twist here. If you do it, that's great. But if you don't, technically speaking, it should be there, but I'm not really going to check carefully for that. What I'm going to check is the general idea. So if a student graphs this and a second student graphs this, I'm probably going to mark it the same. Technically speaking, this is better because the cubic there shows that there's a twist. This looks very much like x minus 5, x minus 10 squared, x minus 15 to the 1 versus to the 3. So what is the difference? A little bit of a twist here. There's more difference here, which we're not going to address. Yeah. So here we got 5, 10, and 15. And we bounce off the 10 because we got double. Every time you got double, fourth, sixth, any even multiplicity, we're going to bounce off. Yeah. The other thing I wanted to talk about is the intermediate value theorem. Intermediate value theorem. This is a weird theorem for many of us because it deals with the existence of a solution or a zero. So this theorem, okay, talks about the existence of a zero, which is kind of weird because we don't ask ourselves, does something exist? Is there a solution? Does a solution exist? Oftentimes when we are looking for a solution, we just go for it. We find it. We don't pause and ask, hey, is there a solution? Or that's a little bit philosophical, it's kind of like, do we exist or not kind of thing. It gets a little out there. In mathematics, however, it is very important to establish whether a solution even exists. We reflect more on those kind of things as math people. Let me exaggerate, because what I'm going to say is not 100% true, but let me exaggerate. Engineers, many times, they don't worry too much about whether something exists or not. They just try to find a solution, and then they move on. And again, I'm exaggerating. I'm not saying that engineers never do that. Of course, there is an overlap, and most of us have a little bit of engineering and a little bit of math. Most of us have a combination. But if we were to exaggerate the two, then engineers typically just go for a solution, and that's it. And with good reason, because when an engineer is working on a project, they usually have 100 problems in front of them. They have to look at the supplier and the costs and whether it is a good way to build something or not, and prototypes. They have, and not to mention, they have employees or workers that actually put together whatever they're working on. They have hundreds and hundreds of problems. So they cannot dwell on one little thing. Oh, does this exist or not? I mean, again, I'm exaggerating. I'm not saying they do that all the time. I'm exaggerating. On the other hand, math people oftentimes think about, oh, is there a solution? Is the solution unique? What are the conditions under which we have a solution? If we change the conditions, how is the solution going to change? We ask those questions periodically, which is in contrast because we're focusing on one problem. An engineer has hundreds, thousands of problems. So there's a difference in the way we think. And that is a good thing. We need both of those thinking. We definitely need both. You know, without engineers, we wouldn't have air conditioning or heating or, um, transportation and electricity and all the things that make our lives very comfortable, very, very comfortable. So that is super duper important. So we need engineers and we need math people. We need both. And again, I'm exaggerating the difference. In reality, most of us have a blend of the two. We're not all the time 100% engineer and we're not all the time 100% math people. I'm just exaggerating the difference so that we can differentiate the two thinkings. Anyway, so the existence, so be aware that existence, we don't typically ask ourselves existence. It's kind of like asking, remember in another video, we spoke about a line being parallel to itself. You know, we don't typically compare things to themselves. That's kind of a weird thing to do, but we do it in mathematics. Same thing with this idea of existence. We ask frequently in mathematics whether even a solution exists or not, under what conditions, under what domain, and so forth. Anyway, let me tell you the practicality of this. Oftentimes, we know there is going to be a zero somewhere, okay? So we know there's a zero, but we do not know where it is. Well, and this is kind of simple. If you have a polynomial function and at one end of the polynomial, at one input, say B, you get an output that is positive. And at the other end, say A, you get an output that is negative. Then somewhere in between, there's got to be a solution. And you may be thinking, isn't that obvious? Yes, it is. But mathematics is very, very formal. We have to establish that this is the way it is. Yeah. So I'm going to give you a narrow statement of the the intermediate value theorem. So this is not the way we write it in calculus, but it works. Okay. So assume f is a polynomial function. Polynomial function. So that means that the domain is all real numbers. Polynomials don't have an issue with domain. Also assume f of a is, well, f of a is positive. I was going to say positive, but let's make it even more general. F of a I think I ran out of this. And f of b have opposite signs. That means one is positive and the other one is negative. Which one is the positive and which one is the negative? We don't know and we don't necessarily care. Then there is a number C between A and B such that f of C is equal to 0. Yeah. So let's do an example. A kind of simple example. 18. So example 19. Okay. Say we have f of x equals x cubed plus x plus 1. I know this graph has an end behavior on the right up and an end behavior on the left down because it's a cubic. So it has this kind of behavior. Is there a root? Is there a solution to this? Is there a zero? And the answer is yes. Where is it? I don't know, but we can establish a narrow window where that solution is using the intermediate value theorem. And the way I start doing this is in a practical way is with a table. And I'm going to put x and the output f of x. Okay. If x is positive, this is invariably going to be positive. So let's say we got 2. That's going to be 8 when we cube it, plus 2 is 10, 11. The output is 11. If we put 1, 1 plus 1 plus 1, 3. So that's not giving me a lot of information. What about 0? 0 plus 0 plus 1, 1. How about negative 1? Negative 1 cubed is negative 1. Plus negative 1, that's negative 2. Plus 1 is negative 1. Let me just write that down to make sure we understand it. F of negative 1 is negative 1 cubed plus negative 1 plus 1. Well, negative 1 cubed is negative 1 minus 1 plus 1. That is negative 2 step by step plus 1. And that is negative 1. That's how we get this negative 1. Aha. I see that this output is positive and this output is negative. So what we can say for sure using the intermediate value theorem is that there is a solution. There's a 0 of this polynomial somewhere between negative 1 and 0. Mind, not between negative 1 and 1, between negative 1 and 0. So if there is 0 and there is negative 1, I know the graph is going to go this way. What's going to do after or before, we don't know. But I do know that, and it's not going to be in the middle. This picture may be a little misleading. Where in between negative 1 and 0, we don't know. Not necessarily at negative 0.5. I don't know where. But we know there's going to be a solution between negative 1 and 0. So there is a solution in between negative 1 and 0. That's what the intermediate value theorem says when applied in this way. Again, that's a little bit of a weird thing to do because the engineering thinking, and again, I'm exaggerating, the engineering thinking is about, okay, let's find that solution as close as possible to it. Let's use a computer or a program, or let's use a graphing calculator. The graphing calculator can figure this out with a lot of accuracy, with a lot of precision. Not the perfect exact answer necessarily, but it will give us just about almost perfect. Not exactly perfect, but close. Yes, but in math, oftentimes, and there's actually jokes about that because math people are not, as they say, as practical. So the math person would say, well, there's a solution between negative 1 and 1. And again, I'm exaggerating. There's a solution between negative 1 and 0. We know that it is there for sure. And then we just move on. All right, I think this does it for now. Don't forget the limit. Again, there are 4 cases, going back to end behavior. There's one more thing. I want to go around and come back to the end behavior. So on the right, you can have the limit as x approaches infinity equaling either infinity or negative infinity, but not both. Not both. But you can have neither. So there could be a case where it's neither one of the two. Okay. But with polynomials, we have to have one of those two for sure, with polynomials in general. On the left, we have the limit as x goes to negative infinity. Whoa, I missed the notation here. I messed up the notation. That's bad. We have to have an f of x here. F of x equals either infinity or negative infinity but not both. But not both. Yeah, and this is true. We'll have one of those two for sure if the function is a polynomial. There's one asterisk I need to add here with domain negative infinity to infinity. So that means if we don't have any restriction of the domain, then we will have what I would call a natural domain or implicit domain, which will be from negative infinity to infinity. And then we have to have on the right, up or down, on the left, up or down. And those are the only two choices for the right and for the left. So don't forget the end behavior. And I think we'll stop the video here.